Okay, welcome back to this first exploration of log functions. We learned about some properties of log functions called cancellation laws, and that's pretty much all we need. We just need to know the cancellation laws. For now, we'll talk about log properties in a moment. And then we introduced these two new operations called exponentiation and logging. We're going to use those operations, those exponentiation operations and logging operations, in order to solve problems like the ones on this slide. I'll show you what I mean. So in this first problem, problem A, we have log base 3 of x is equal to 2. And what I'm going to do is I'm going to exponentiate both sides. When we do exponentiation, we say the left-hand side to a power is equal to the right-hand side to that, some power to the power of the left, some number to the power of the left-hand side is equal to that same number to the power of the right-hand side. We can pick any number that we want because we want to use the cancellation law. Because we want to use the cancellation law, one particular base is going to be valuable. Any other base won't help us. The base of the log function is the base that we want to use for our exponentiation. So I'll say with base 3. So this is what that means. I'm going to take the left-hand side and raise it to as a power on 3. I'm going to take the right-hand side and raise it up as a power on 3. So 3 to the power of log base 3 of x equals 3 to the power of 2. So we exponentiated, we raised both sides as powers on the same base. And because I used a base of 3, we can use the cancellation law. And what that tells us is that, so all that's left is x is equal to 3 squared, which is 9. And that's it. So the big things are this new operation called exponentiation and the cancellation law. And we're doing the exponentiation in order to get access to the cancellation law. And why do we want to do this? Do you see that log function? Do you like the log function? No. We want to get rid of it. That's what this does. This eliminates log functions. We're desperate to get rid of them and get back to exponentials because they're way better. Next one. We're going to do the same thing. I'm going to raise both sides as a power on a different base. Or it's actually the same base, base 2. Exponentiate with base 3. So I have 3 to the power of the left side is equal to 3 to the power of the right side. 3 to the power of log base 3 of x is equal to 3 to the power of 4. And I can cancel 3 log base 3. What do I get? I get x is equal to 3 to the power of 4. 3 multiplied by itself 4 times. 3 times 3, 9 times 3 again, 27 times 3, 81. So what are log functions? Log functions are things we get rid of. For now, we get rid of them as soon as possible using these rules, using exponentiation and cancellation law. That's what logs are, things to eliminate. Now, they're going to be something that we actually use, something that we introduce, but for now, we hate them so much and they're so new, we want to get rid of them as soon as possible. Okay, the next one. X equals log base 3 of 9. There's two good ways to do this. I'm going to do the first way down below. Now, I put using cancellation law, so I'm about to show you a way that does not use the cancellation law. Oh, I lied. It does, but it's different than what I was about to do. Log base 3. Can you write 9 as 3 to a power? Yes, you can write it as 3 to the power of 2. I now use the cancellation law. Log base 3 of 3 to the 2 equals 2. Now I'll show you another way. It's the same way that we just did. Not as good. We're going to exponentiate with base 3. It's kind of circular this next way. I miss having you in class, because in class the hand will go up. Why are we picking 3? Because it's the base of the log. We want to match the base. Why do we want to match the base? Because that's the only way we can cancel. If the bases don't match, we cannot use a cancellation law, which I probably haven't said yet. But they only cancel if the bases are the same. If the base of the exponential and the base of the log are the same number. So 3 to the power of log base 3 of 9 equals 3 to the power of x. So this cancels. I have 9 equals 3 to the power of x. Well, I can write 9 as 3 squared. 3 squared is equal to 3 to the x. And what does that mean? Well, that means x is equal to 2. So this is an alternative method. Definitely smarter. Also uses the cancellation law. Just wanted to show you that there's more than one way to do these things. How about the next one? So what are you going to do? Can you write 3 as 9 to a power? And yeah, you can. You can say that this one here is log base 9 of 9 to what power? 9 power 1/2 is equal to x. And use a cancellation law. And we get x is equal to 1/2. So that's good. That's a perfect answer. I'm going to show you a second way. It's more work, but it follows the same template as the other ones. We're going to exponentiate. We have 9 to the power of log base 9 of 3 is equal to 9 to the power of x. And then cancel. Since the log base and exponential base are the same, we have 3 is equal to 9 to the x. And now we have to make 9 equal to 3 squared. Make the bases the same, so 3 to the 2 all to the x. So 3 is equal to 3 to the 2x. I'm going to put a 1 here. So 1 is equal to 2x. And what does that mean? That means what we got above is correct. Using the second method, x is 1/2. Okay, the next one, I'm going to do the exact same way. I'm going to exponentiate, raise both sides as powers on the same base. And what base do I use? I use 16 because I want to match the base of the log function so I have access to this cancellation law, which destroys log functions. 16 to the power of log base 16 of 4 is equal to x. And I can cancel. Oh, sorry, equals 16 to the, I forgot to do the other side. You want to do both sides, or otherwise you've destroyed the equal sign. Whatever you do on one side, you have to do the other side. So I'll raise the left side to 16 as power on 16. I have to raise the right side as a power on 16. So now I have 4 equals 16 to the x. Well, I have to use something very similar to the previous one. I have to replace the 16 with 4 to the power of 2. Multiply the powers together, so 4 to the power of 1 is equal to 4 to the power of 2x. 1 equals 2x, and then that means that x is 1/2. And we could have done this one in a smarter way. We could have just said that 4 is equal to 16 to the 1/2 and use the cancellation law. It's log base 16 of 16 to the power 1/2. So cancel, you just get your 1/2, just like the one on the left, just like part D. Okay, last problem. What am I going to do? I'm going to raise both sides as powers on the same base, and I'm going to match the base of the log function. So x to the power of log base x of 16 is equal to x to the power of 2. I have x to the power of log base x. That's going to cancel. Even though it's x, it doesn't matter. The bases are the same. The base of the exponential, the base of the log match. So 16 is equal to x squared. And what we get is x equals minus 4, and x is equal to positive 4. But one of those solutions is incorrect. This one's correct. Why is the negative one incorrect? And the answer is we're not allowed to have the log function with a negative base. Log functions can only have a positive base, just like exponential functions can only have a positive base. Notice that x is in the base of the log at the very beginning in the original problem. The most common bases of log functions are base of 10, because we have 10 fingers. Our number system is base 10 for the same reason. There's nothing otherwise special about the number 10. And the other base that is special is base E. E is this extremely special number discovered, as far as we know, by someone trying to discover or trying to understand compound interest, and it is expressed in the sciences and social sciences. It's hard to escape. It's encoded in the DNA of the universe. Because it's natural to the universe, we call a log function with that base the natural log function. And because doing math with base 10 is so common, we call log base 10 the common log function. If you have a calculator, which I'm supposed to have a calculator somewhere, but it's been stolen by small children, and I think used as a pretend cell phone by my 3-year-old. But if you had a calculator, you'd look at it and look for log buttons, and you'd probably see only 2 log buttons. You'd see log, L-O-G, with no number underneath it. That means log base 10, and then you'd see another log button, Ln, which means natural log. Ln of x is pronounced lawn of x, like a green lawn of grass. I'm going to continue to call it lawn. I'm not going to call it log base E. It's just it comes up so often, and it's so ingrained in my own mind that I cannot escape calling it lawn. So you're going to have to start calling it lawn too. One of the things that really, so up until this point, up until this slide, a log function is something that we get rid of. We use exponentiation and cancellation law to take an expression that involves logs and convert it into an expression that does not involve logs. So we bring it to happier territory. We translate it from a language that is not something that we speak very well, or maybe we don't speak it at all. We quickly translate it to a language that we're much better with. We translate it from logs to exponentials. Now, what I'm going to show you next is what happens if you decide to spend a little bit more time in log land and you don't immediately translate. Or maybe you can't immediately translate. It's too complicated to immediately translate. So you got to stick there and live there and order food there and figure out how to ask for directions there. So these rules of log functions are the rules that dictate how log functions operate. And they look extremely bizarre. Like the first rule, log base b of m times n being equal to log base b of m plus log base b of n, that looks completely arbitrary. And actually it's not. I'll tell you where it comes from. It comes from one of the exponent laws. It comes from this one. It comes from b to the m times b to the n is equal to b to the m plus n. It's actually the translation of that law into the language of log functions. Like these things really are, like math is really a language. It's actually a set of languages. And it's not an overstatement to say that it is a genuine translation from log functions to exponentials or exponentials to logs that also allows us to translate the rules from one to another. How about rule 2? Log base b of m divided by n is log of m, log of the top minus log of the bottom. Take a wild guess where that one comes from. That one comes from b to the m divided by b to the n is b to the m minus n. It is the analogous log rule to that exponent law. Now the next one is the translation of this rule. B to the m all to the n is equal to b to the m times n. Rule 3 says if you have a log of any base of something to a power, you can bring the power down in front. This looks a little bit like a derivative, and it's not. There's no connection at all to derivatives. It's just a translation of the b to the m all to the n is equal to b to the m times n. It's a translation of the exponent law into log language. The next two look weird, but they're not. If you want to know what the corresponding log or the corresponding exponential rule is, for log base b of 1 is equal to 0, so log of 1 is 0. And I put that in quotes underneath. Log of 1 is 0. That's what that rule 4 says. You plug 1 into a log function, you get 0. Looks mysterious, but what that means in exponential language is that b to the power of 0 is equal to 1, which isn't mysterious at all. We've been talking about that from the beginning. How about the next one? Log base b of b is equal to 1. See, if you take a log function with a base, and into that log function you plug the base, a 1 comes out. And we've already seen this. We saw an example of log base 99 of 99 is equal to 1 because we just recognize that there's a 1 up there. If there's no power, that we use the cancellation law. But what does this mean in terms of exponentials? What does the corresponding exponent rule mean? And this one's like, this is a big shocker. It's b to the power of 1 equals b. So I'm kidding, it's not a big shocker. Like that, 2 to the power of 1 is equal to 2. 5 to the power of 1 is equal to 5. It's totally non-profound. It's not interesting that something to the power of 1 is just itself. But it looks so much more profound and so much more scary written in the language of logs. And the only reason it looks scary is because we're not used to this language. We don't live here. We're tourists in log world. And I'm still a tourist in log world. No matter how, when I'm 100 years old, if I live that long, I'm still going to be a tourist in log world. Because I didn't grow up in log world. No one grows up in log world. We're thrown into log world, kicking and screaming, and we learn to live there. The last rule here is a combination of exponent rules. And it is a statement for the conversion of a log function. So it's a base log base conversion. It is a statement that allows you to convert a log function with one base into a log function with a different base. Because let's say you want to find log base 7 of 10. So you whip out the calculator and you're like, I don't have log base 7. I don't have like a log function that allows me to pick the base either. I have log 10, or just log, which is log base 10, and I have log base e. So are you telling me I can't do log base 7 of 10? And the answer is absolutely you can, but you have to do it as follows. Log base 7 of 10 is equal to, so I'm going to pick ln. It's the ln of 10 divided by the ln of 7. I also have to apologize that my L's when I write ln are curly because I learned how to write with cursive. And I unlearned how to write with cursive, so I print for the most part, so that no one questions my cursive writing. It wasn't very neat, but no one learns cursive isn't learned anymore, so I don't want to write with cursive. Except my L in ln, not in log, only in ln, and I don't know why. I'm so sorry. I can't make it go away. We're stuck with that. So what will you do with the calculator is if you want log base 7 of 10, you do ln 10 divide ln 7, hit enter, make sure the bracket's in the right spot, and what gets spit out is the decimal representation of log base 10 of 7, and that's the only way you can do it. You could also use log base 10 instead of ln, because you also have that button, and it'll give you the same decimal representation. We'll continue in the next video using some of these rules. And I know it's hard, I know it's weird, I know you're not happy inside this new log world, but we'll figure it out. It'll be okay.